that DeepMind had provided, and there were no commercial restrictions whatsoever at the time. Nonetheless, when they did release AlphaFold 2, they did not provide the training code, and so it wasn't possible to take it and train it on new data. With AlphaFold 3, they've actually been even a bit more restrictive, right? They haven't released the model weights of the code yet. They say they will, but for non-commercial purposes, I'm assuming they won't be providing the training code. And I think for AlphaFold 3, it becomes even more pertinent, actually, because we're talking about small molecules and sort of chemical space that's more restricted and maybe more proprietary in some cases. So with OpenFold, the work, the code, we essentially set out to build a trainable implementation of AlphaFold 2, right? That's based on PyTorch, so a more sort of commonly used system. And as I'll show you, we I think succeeded in sort of fully reproducing it from scratch, including achieving parity performance-wise. And what we're excited about more broadly is using this as a platform to build new capabilities, including things like AlphaFold 3 like capabilities. And incidentally, the paper just came out this week, so sort of good timing as well. In Nature Methods, you're welcome to take a look. This was, I should say, a very large community effort from people in my lab and in the broader community, including contributions from Microsoft, NVIDIA, and Amazon. So it was very much kind of a team effort. But just to kind of orient you, so it does work. So what I'm showing here is essentially a scatter plot of AlphaFold 2 versus OpenFold predictions. Each dot is an individual protein, and what you'd like to see is that most things lie on the diagonal, meaning that when one method does well, the other does well, and and conversely, when one does badly, the other does badly. There are a few sort of outliers in both cases, in instances where OpenFold does better than AlphaFold 2 and vice versa. And this is largely just from stochasticity, either in the kind of inference procedure or the way the model is trained. So nothing to kind of worry about. But in expectation, the models are essentially identical. And you see kind of an example of this, visualization of this in a way, where the white is the PDB structure, blue is the AlphaFold 2 prediction, and pink is the OpenFold prediction. And you see there's kind of very high superposition between them. So that was nice, but somewhat surprisingly, actually, when DeepMind built the system, I think they left a lot on the table in terms of optimizations. And so we were able to make the system actually work better in terms of speed and memory efficiency. Again, much of this was in collaboration with other folks. So the code that's currently available, this is kind of the latest version of OpenFold, is actually considerably faster than DeepMind's code. It's 3 to 4 times faster, depending on the length of the protein. And again, this is with perfect parity. So in fact, you don't even have to use sort of our weights, our model weights. You could use the DeepMind weights, so you get the exact same model that they had, put them into the OpenFold code base, and we have essentially kind of semantic identity between those two systems. So even though they're two independent code bases, you could take model weights from one system, put them in the other system, and just have it work out of the box. And what we also support is a longer chain, so you can infer a much larger proteins or protein complexes than you could with AlphaFold 2, including something like 6,200 residues, I believe, on a single GPU with like 80 fairly beefy GPU, but a commercially available GPU. We've also sort of made it easier to train the system from scratch, over the last year or so that we've been working on it. Memory consumption has actually been reduced considerably, which allows, in particular, larger crop sizes. So this is a bit in the details of how the system is built. But typically, when we train OpenFold or AlphaFold, we don't train on full-length proteins, but on essentially fragments of proteins. This is particularly true with complexes. And so now we can train on up to 1,200 residues, which is rather considerable, and we expect will help in terms of generalizing to larger complexes and assemblies. And things like model parallelism across multiple GPUs and so on. So basically lots of sort of quality of life improvements in being able to kind of deploy this. And I think we actually still think there is benefit to do this, particularly if you're pharmaceutical, have proprietary data where potentially, if you're working on kinases or GPCRs or transcription factors, potentially fine-tuning OpenFold on those data sets would be valuable, and this obviously allows you to do that. But more broadly, moving forward, I think as we move into other types of chemical spaces, including small molecules, I think this becomes all the more pertinent, as I said earlier. And maybe this gets a bit into the weeds, but just again to say, we've also sort of improved the robustness of training these systems, so you could essentially use much lower precision. So if you have kind of modern GPUs, H100s, A100s, you're able to actually kind of accelerate training even further using lower precision, which could make a big difference. I guess by way of reference, I should say that sort of a full training run of AlphaFold 2 from scratch, all the way to the final stages of fine-tuning costs about 200,000 GPU hours. So it's not an inconsiderable investment. investment, so being able to kind of do this more efficiently is obviously helpful. All right, so now let me kind of step back a bit and then give you the sort of status update of where the field stands. And what I'll do, I'll kind of walk you through 5 main areas, which I think are kind of represent maybe many of the things that we want to do with machine-learned kind of biomolecular modeling. I will, in some cases, talk about AlphaFold 3, depending if it's relevant or not, and in some cases talk about OpenFold if it's relevant or not. But this is somewhat of a kind of a, like I said, a survey of where things currently stand. So let me start actually with the result that we had from the OpenFold work, which I think is interesting, and I think many people are not familiar with. So like I said, we had these very beautiful Cas14 results. They were very impressive. But in those instances, DeepMind trained AlphaFold on the entirety of the PDB. And even though we do see occasionally novel folds in Cas competitions, the fact of the matter is, fold space is pretty darn saturated at this point, right? So this was not necessarily a particularly good indication of how well the model generalizes to essentially unseen regions of protein structure or chemical space, right? And so we set out to test this because we could train the system from scratch. And what we first started out with was to say, what if we just take the data set, the PDB, and instead of training on all of it, just subsample it to smaller and smaller fractions, and then assess how well the model does as a function of training time. So what I'm showing you here are training curves, where the x-axis is basically how long you've trained the model for, and the y-axis is LDDT, which is a metric of structural quality, 0 being very poor, 1 being very good. And the pink line, the kind of the topmost line, this was a model trained on the entirety of the PDB, so this is kind of the upper bound. This is how well you expect a fully trained AlphaFold 2 model to do. And then as we kind of go down, so the percent remaining indicates what fraction of the PDB do we retain, right? So we're taking smaller and smaller chunks of the PDB, and then we're training on those smaller chunks and asking how well does the model do, right? And what's remarkable, right, so when you go down to all the way to 0.76 or whatever, it does dip, certainly. But what's interesting, let me see if this works. It does work. So if you look at the sort of teal curve, which is, I think, about 1.5%, so here we're talking about, literally something like 2,000 structures, right? So really a small fraction of the PDB. This model, right, it achieves an LDT of about 0.7. And the reason why I think this is really remarkable is because if you look at AlphaFold 1, the system that came 2 years before and made a splash in its own right, that system actually achieved an LDT of 0.6, right? So this AlphaFold 2 model, trained on essentially 1/100th of the data that AlphaFold 1 was trained on, surpasses its performance. Right? And I kind of make this point is because it sort of indicates, I think there's often a discussion about data versus models, and do we need model architectures, or is it just transformers all the way? I think this is a clear indication that model architecture and innovation makes a huge difference, right? That AlphaFold 2 is essentially 100 times more data efficient in being able to extract information from corpora. And I think, particularly as you think about new chemical modalities, I really think this becomes even more pertinent, right? And incidentally, as I get to AlphaFold 3, I think we essentially saw the same thing play out again. Particularly when you compare sort of Rosetta Fold all atom versus AlphaFold 3, you see that kind of the value of architectural innovations and how much of an impact they could have. Now, with this particular kind of split, right, here we just did random subsampling. And so one could convincingly argue that diversity-wise, you're still seeing a very diverse set of folds, and so maybe you don't need that many structures because you just see them over and over again, but so long as you have a representative kind of distribution from fold space, you're good, right, and that's what really matters. So we tried to get at this question by using the Cas classification, which essentially stratifies structure space into kind of a hierarchy, all the way from like class, which corresponds to essentially alpha helical versus beta sheet proteins, all the way down to topologies, which are much finer grained sort of delineations of structure space. So we begin with topologies, right? And this you could think of as essentially clustering all of the PDB into like 100 clusters, right? So if you think of the structural diversity that you know of, and you sort of partition it down to 100 representative kind of groups, that's what topology indicates, or what topology operates on. And interestingly, so now when the percentages don't no longer correspond to number of structures, but to number of topologies, right? So when we're training on 5%, that means we're training on 5% of the kind of topological groups in the Cas classification. And so again, we see a similar thing, right? Where particularly on, like, say 10%, right? This is a significantly less performant model, to be sure, but again, more performant than AlphaFold 1, and already by 50%, you're essentially back at parity. And what's remarkable is that this essentially holds all the way up to classes, right? So in this instance, right, the magenta is indicating a model that was basically trained on almost exclusively alpha helical proteins. So maybe there are a few beta strands here and there, but for the most part, this is only seen alpha helices, right? And we're assessing its performance across the board, right? And similarly on the beta trained model. So these are really severe kind of tests of generalization, right? Things where, talking about out of distribution generalization, this is an extremely severe test of that, right? And this is actually kind of a visual example of this, right? So the top model is one that was trained on alpha helical proteins. The oranges are kind of ground truth structures. This prediction here is the prediction of this structure coming from the alpha helical trained proteins model rather, so not surprisingly does quite well. But this prediction is one coming from a model that's only trained on beta sheets, right? So it's never seen alpha helical proteins. And yeah, sure enough, it's kind of hallucinates a strand, a couple of strands here when it's not supposed to, but in general, it doesn't look terrible, right? And conversely here, this is a model trained on beta sheet proteins. It recovers this prediction very well. It misses the secondary structure elements. It doesn't quite get the right hydrogen bonding network to like pi mole see this in secondary structure elements. But the C alpha trace is more or less in the right place, right? So it recovers the overall geometry. So again, this, I mean, for me, I will say this is really, really surprising. I had expected the model to completely kind of fall apart when we would sort of stress it in this way, but it did not. And so I think it does indicate that this model is learning something very, very non-trivial. I'm happy to sort of speculate a little bit more on this during the discussion in terms of how it may be able to do this. But I do think this is a kind of a good sign in terms of our ability to generalize. Right. Okay. So that's it. So that's it for monomer. So this, in a way, it was kind of a positive story. This is an example of where it does really well and is able to generalize very well. Mutations, the second one, is the opposite. It's really a very negative story where essentially kind of the state of the art is that it doesn't work, and it doesn't even sort of partially work. So let me kind of just describe a bit of why we think it doesn't work, right? So many of the performance methods, right, the ones I showed you just now, are essentially multiple sequence alignment based, right? They require multiple sequence alignments to make predictions. They look into the evolutionary history of these proteins and how they covary across time, right? So what this essentially means, right, is that they're averaging out in a way, right, sort of conceptually, the variation within a protein family, right? And so conversely, what this is doing in a way is that it's almost adversarial to how what the interesting predictions or the interesting problems are doing or presenting to the model is an adversarial problem, right? Because what we care about are mutations that are structurally disruptive, that change it in some way. And so they almost in a way violate the underlying assumption beneath an MSA, which is that all this variation across evolutionary space does not change the structure materially. Right? So you're presenting it with a kind of a task that was almost trained to not only ignore, but to sort of work against, right? And obviously, as far as we can tell, hasn't really changed anything here, unfortunately. Now, protein language models, I think maybe some people thought, including myself, I will say, that they would sort of address this. So if you're not familiar with protein language models, let me just kind of quickly mention what they do. So this is an instance of one, ESMFold. The basic idea is that you do this exercise where you sort of train in a self-supervised way on lots and lots of sequence data, a bit like ChatGPT works. You take a sequence, you mask certain residues, you hide their identity, and then you try to recover the identity of the masked residues just through this kind of self-supervision task, typically trained on hundreds of millions or tens of millions of protein sequences, a very large scale. And so what the ESMFold model did was basically took this ESM2 model, this kind of protein language model, fused it to OpenFold, and then by jettisoning the MSA component, right? So there's no MSA anymore. There's just sequence, a protein language model embedding, and then the prediction. And I think the hope was, at least for me, and I think other people in this space, was that this sort of approach would allow us to actually model the impact of mutations well. Because incidentally, I should say, these models are actually not, these models are not terrible at capturing the impact of variance, right? So they're actually pretty decent, for example, thermostability predictors. They're pretty decent pathogenicity predictors, right? So they do seem to capture something about how individual residues alter the fitness of a protein, let's say. And so it's not entirely crazy to stand to reason that they may have some information that's of value to protein structure prediction. And they certainly do in the sense that because, for example, it's not using a multiple sequence alignment, it's much faster than AlphaFold 2. So at the time, this was part of Meta, now it's a separate company. But at the time, Meta applied it to the metagenome and predicted like hundreds of millions of structures. That would be very, very expensive to do with AlphaFold 2. So it certainly has some utility. But when it comes to the task of predicting impact of mutations, it didn't really do very well. So this is a bit of a complicated graph, so let me walk you through it. So here we're looking at Cas15 targets. So those are individual protein targets at Cas15 that assessors try to assess. And they are ordered by what's called the N effective. This is essentially the depth of your MSA. So how well characterized evolutionarily is your protein? High being high, so you have a lot of evolutionarily related sequences, and low being potentially orphan proteins for which you have no homologs. And so here's what's interesting. So the blue, if you can see them very well, it's a little bit hard to see, but the blue curves, like here, these are predictions coming from an MSA-based method, the kind of conventional methods, right? While the red curve is coming from ESM-fold, or methods like it, so protein language model-based methods. GDTS, so 100 is good, 0 is bad, so you want to be as high up as you can be. Now, what's interesting, generally speaking, they seem to track one another reasonably well, so they do about the same, irrespective, which is maybe good or bad, I suppose. But particularly, as you go to the low MSA regime, right, so this is where you have low sequence homology, it actually seems to be the case that the PLN-based methods, the ones that use language models, do worse than the MSA-based methods, right? So almost the opposite of that underlying hypothesis, right? That protein language models seem to essentially be worse at capturing regions of sequence space that are not well represented by an MSA. And what in partly it suggests is that when a protein language model sort of learns from sequence space, it's learning essentially in proportion to the density of sampling in that region. And so if it's sparsely sampled, it doesn't learn very well, which is not so good. So this is a bit of a negative result. Like I said, we had, I should say, sort of our own effort on this called OpenFold Seq, which sort of does kind of a similar thing. It's not been publicly announced yet, actually, but it is available on GitHub, so you can download it and use it if you want to. It is similar to ESM-fold, the method I just described, but it incorporates templates, so you are able to present it with a template. It's the same. It suffers from the same issue in terms of the insensitivity to mutations, but it does allow us to introduce sort of a new application or to enhance an application, which is quite nice, and that actually does better than AlphaFold does on this application. And that's this notion of an AF rank. So let me just kind of walk you through it because I think it might be of interest to this community. So this kind of idea was introduced by this paper from Ovchennikov's group, where the basic notion right here is that what AlphaFold 2 may be doing, right, is that it may be using the MSA to essentially sort of sculpt its overall energy landscape, and particularly to sort of identify where in that energy landscape is the global minima, roughly speaking. Then essentially uses something like the structural module, or it doesn't really have to be the structural module. I think this is distributed through the entire system. It's using something like implicit physics, something that's sort of learned from having seen so many PDBs, right, so many PDB structures, to then sort of go from this kind of overall, minimal region to the actual local minima, right, to sort of the final optimization. So it's, this is all conceptual. This is all, intuitive. This is not meant to be literal. But this, I think it's a reasonable kind of articulation of how AlphaFold 2 may be working, right, is that there's a kind of an MSA-based kind of piece which can sculpt the overall landscape, and then that kind of an implicit physics piece that gets you down to the local minima. So one way to assess this, and this is what they did in this paper, which was quite nice, was to strip out the MSA. So don't give AlphaFold an MSA anymore, but instead hand it a template, so a structure that may look like the structure you're trying to predict, or that may look very different. Right? So you could essentially scan it with a whole bunch of different decoys, right, at varying levels of similarity to the ground truth structure, and that's what the x-axis here is scanning, and then the y-axis is essentially how happy AlphaFold 2 is with that given structure. Right? And so what's interesting here, right, and I think this is by no means obvious that this would be the case, is that it's actually pretty well correlated, right? So what this indicates is that AlphaFold 2 is a pretty good scoring function, right? That given a sequence and given a structure, AlphaFold can essentially tell you how happy is it with that structure, that how good a fit is that structure to the given sequence. And you can imagine all sorts of applications for this sort of thing. So this work was done based on AlphaFold 2. Now, like I mentioned, we sort of built out this new system, but when we take the same approach with this kind of AF2 ranking approach, and then apply it using this OpenFold seek methods, we actually see considerably improved performance. So there's a lot of curves here, I realize, but this is the AlphaFold 2 with the no MSA with template scheme that I just mentioned, the AF2 rank approach, and this is the GDTS that it achieves, and we see a rather big bump with this approach, right? So this suggests that we have an even better scoring function now than AlphaFold 2 did. And like I said, this is not published, but you could actually download it from the GitHub and use it if you're so interested. So we also noticed, so actually let me just describe how the method works in a second, because I think it's confusing. So the way we do this, essentially, is we take the AlphaFold 2 architecture, which I'll come back to in a moment, and ablate the MSA piece, and replace it with a protein language model like I just talked about earlier. So quite similar to how ESMFold works. What's interesting now is if we look at the training behavior as a function of time, I mentioned this kind of training curve where we see how well the model is trained as a function of time. With standard AlphaFold, right, what we see is that the model learns very rapidly, but then it takes a very long time to essentially kind of saturate and sort of get fully fine-tuned. But much of the performance seems to come in the early phases of training. Right? This is kind of vanilla AlphaFold 2. If we assess it now on this question of AF2 rank, where we're trying to see how good the scoring function is, and when we look back at essentially this figure, right, that long curve, what we see is that for much of that long curve, right, when it seems to have saturated, in fact, its implicit physics function is quite poor. Right? So the axis is changing a little bit, but the 12,000 here is essentially like here. Right? So by now, it looks to have already saturated. Right? But if you look at the implicit physics function, the one I just showed you earlier, the correlation value is actually quite poor. So it takes a very, very long time, right, from this to about 200,000 steps to finally reach that saturation point. So this suggests that AlphaFold actually has two distinct phases of learning, where in the initial phase, it essentially learns to use MSAs. And that phase is like 5% of the training. And there's another 95% where it learns to acquire its implicit physics function, which is quite interesting. And may also kind of suggest ways in which one could re-architect this approach to get it to work better as an implicit physics function. So with that in mind, in fact, we are trying to do just what I described, where we are, again, removing the MSA, but now no longer using a protein language model, but instead trying to go directly from sequence to structure, to building kind of a true sequence to structure model as opposed to an MSA to structure model. And the way we're doing this is essentially through kind of massive cross-distillation, where we're using predicted structures to sort of bootstrap the process. And again, this is all unpublished, but what's interesting here, just to kind of give you a sense of this, with a very simple model that's not modified in any way, so it's not really trying to reflect this kind of implicit physics learning, just a vanilla AlphaFold 2 architecture, we're seeing a model that certainly requires a lot to train, but that begins to actually hit numbers that are not quite AlphaFold 2 level, but certainly considerably better than AlphaFold 1. Right? So this is a model now that does not rely on MSAs in any way and does not use protein language models in any way. This just goes directly from sequence to structure. We do think that this model will be better reflective of things like mutations and so on, but I won't have, I'm not going to show you any sort of results on that front. But we do think it's kind of an interesting approach to try, and quite parallel to, or orthogonal to AlphaFold 3 rather, that gets at the problem from a kind of different angle. Okay. That's it for mutations. Now let me give you kind of more of a bit of a mixed story, although I think for the most part fairly positive, which is a question of multimers and complexes and protein-protein interactions. So at Cas14, this is when AlphaFold 2 debuted, the accuracy of most predictions were quite poor. So there are so many different metrics, I'm just going to keep switching between them, but basically 0 is bad, 1 is good. What you see here is that most complex predictions at Cas14 were in this kind of red region, so they're quite poor. So the interface of the complex was not recovered doing those predictions. At Cas15, we saw a massive leap, right? Where that 4 was almost, where the red region almost completely eliminated, and then most predictions were either well predicted or at least moderately well predicted. So a really kind of big leap forward into our ability to predict complexes. And this is, you could visualize it a little bit differently, where if you look at easy targets, everyone even all the way back to Cas12 was doing well on them, but it's the hard targets where at Cas15 we saw this really big gain in accuracy for their predictions. And if you look at individual examples, so these are again Cas15 targets, these sort of cyan, or not cyan, rather, beige circles were AlphaFold 2 vanilla predictions, AlphaFold 2 multimer. And then the blue triangles were the best predictions at Cas15 coming from different methods. But you can see, really massive leaps over AlphaFold 2 multimer. So, pretty large gains. So what's the secret sauce? There actually wasn't a single idea, but there were some simple ideas. And one of the most interesting was from a single person, Wallner, what he did basically was to generate many samples, so generate many predictions, not just one, but inject noise in the prediction process so that the model is predicting a slightly different conformation every time. And because AlphaFold is self-calibrated, has its PLDT metric that essentially allows it to rank its own predictions. If you make 50,000 predictions, you could then use that metric to essentially pick out the most promising one, the one that AlphaFold thinks is the most performant. So the caveat here is 50,000 predictions. This probably means something like on the order of 50,000 GPU hours. So this is a very expensive thing to do computationally, right? But it's still, if you're really sort of well motivated, this actually gives, this pays some dividends. And incidentally, when I'll get to AlphaFold 3, this sort of approach was actually utilized by them for certain classes of proteins. And incidentally, AlphaFold 2 multimer at the time also made an entry unofficially and did about as well as these methods did without any of the sampling approaches, just simply by using larger crop sizes. I mentioned at the beginning that with the newest OpenFold release, we could train on all the way up to 1,200 residues. In this case, they had bumped up the training crop size to 600, and they already saw these big gains in being able to recover multiple protein complexes. So what about AlphaFold 3? So it's interesting. On monomers, not a ton of difference, not surprisingly. I mean, significant, but not materially maybe important. Proteins, they do go up a little bit. But where you see a massive gain is actually on protein antibody structures, right? Where we see really big gain in accuracy. And one can speculate as to why that is. But one thing I want to point is this idea of sampling, right, and oversampling. So what's interesting here, right, when you look at both low homology antibodies, low homology with either just a fraction of correct or sort of very high accuracy predictions, what you see is that with this oversampling approach, with AlphaFold 2.3, they used to saturate. So past a certain point, it doesn't really pay to continue to sample. But with AlphaFold 3, the curves just keep going up, right? I mean, maybe the slope is not as high as you'd want it to be, but still, there does not seem to be really any kind of saturation in terms of the increase in accuracy as one samples further and further. So this is additional indication that the model has learned a pretty good implicit physics function, right? That's able to score these structures, and that what is struggling with in this instance is actually more the sampling, right? That's able to sort of do enough to finally kind of chance upon the conformation that corresponds to the ground truth structure, right? Okay, getting closer to the end. So conformations is another key question, right? So proteins are not static; they are dynamic, and we want to capture that dynamism. I will say this is probably the area that is received. Well, it's received a fair bit of attention, but maybe it's seen the least amount of progress, at least systematic progress, and I'll try to explain why that's the case in a moment. So already very early on, as soon as AlphaFold 2 came out, people were trying to come up with various ways to essentially kind of perturb it, to provide it, to induce it to predict alternate conformations. One particular paper, for example, took the multiple sequence alignment and simply replaced it with sort of all alanines in particular positions, positions that are known to form contacts that are transient, right? So there's some prior knowledge there. And by doing so, sort of got it to kind of predict an alternate conformation, right? So, a bit of a hack, right? And it requires some prior knowledge, so it's a bit circular, but it somewhat worked. More recent work from Corey Duren's group did this in a bit more principled way, where they essentially cluster the MSA for a protein so that they essentially extract sort of subclusters or sub-MSAs that correspond to regions of the phylogenetic space, right? So the idea here is perhaps in sort of different points in the evolutionary tree, the protein has one conformation preferred over another, and if you sample in this kind of more structured way, you'd be able to sort of extract that conformation. So it's not just sort of random subsampling, but this kind of more phylogenetically informed subsampling. And sure enough here, again, this is for fold switching proteins. They're able to sort of see this switch, or they're able to, depending on which part of the phylogeny, again, they sample, they're able to induce it to give one structure or another. So this is nice in the sense that it's no longer kind of circular, right? It's working kind of, in a somewhat principled way. But the challenge here is that it doesn't really work all the time, right? It works in some cases, but not in most cases. And this is true for all these conformational sampling approaches. They're a bit spotty, right? And they're not consistently working across all protein families. Since then, there's been quite a bit of work on bringing diffusion into the picture. So if you're familiar with like DALL-E 3 or any of these methods that generate pictures of people or scenes or what have you, what's driven much of the progress there is these diffusion models. I won't go into the details of them, but suffice it to say it's sort of an iterative approach that takes an entity and tries to improve it and does so in an iterative fashion. So people have essentially taken the AlphaFold 2 representations coming from AlphaFold 2 and then conditioned on them these latent representations to sample a kind of a diffusion process that is trained on either molecular dynamics data or on PDB, alternate conformations coming from the PDB, with the hope of trying to recover something like a Boltzmann weighted distribution. Again, here, I think it's the same story, I would say. It's a bit spotty. Sometimes it works, sometimes it doesn't work. The most recent work in this kind of vein is AlphaFlow, which I think is the most promising in a way. Again, same principle, conditional AlphaFold 2 representations and induce a diffusion run. And at least in this case, when they trained on MD data, that was very short time frame, short time horizons, not particularly long MD data. They did seem to be able to recapitulate not just recapitulate, but also generalize to new proteins, but also on those short time horizons. So this, to me, I think is kind of the most sort of interesting development. What's also interesting about this is that it anticipated in many ways AlphaFold 3, because as I'll talk about in a moment, what AlphaFold 3 essentially does is something very much akin to this, not for conformational sampling, but just simply to condition on this sort of internal representation to then run a diffusion process that generates a structure. Back to these methods, just one sort of last point to say is that, again, they are still not, however, sort of systematically performant. So one way of measuring this is a precision recall curve, where what you're recalling over is the ensemble that's observed in the PDB, right? So if you consider the PD as providing an ensemble for a given structure, you can ask, well, how many of those conformations that I see in the PDB are recovered by using this sort of approach? And what's interesting here is, if you look at the subsampling approach, the one that I mentioned earlier, that seems to actually run the gamut pretty well, right? And this is a very simple approach, right, where you can trade off precision for recall. AlphaFold, the one I just showed, has pretty decent recall, but it's sort of not meaningfully better than just MSA subsampling. So it still needs to be a challenge to really kind of recover beyond what's seen by AlphaFold itself just by subsampling its MSA. Okay, so now let me get to kind of the last piece, which is a small molecule, and I think is probably the most interest to this group and the one I'll spend the most time on. Let's make sure I'm not running way out of time. I am actually, so let me try to run through this quickly. I'll actually skip diff-doc just because I think it's maybe of less relevance right now, but I'll mention one thing. So there have been studies that show in these approaches they often introduce pathologies in the resulting ligands, right? Particularly on the ligand side, right? Bonds that don't make sense, angles that don't make sense, and so on. And I think this has been sort of very nicely formalized by this paper on this kind of data set called Postbusters, where they essentially assess these various deep learning-based methods before and after controlling for chemical validity, right? So the kind of the salt region of the bar is one that does not account for chemical validity. That does account for chemical validity, and the one that's crossed does not, right? And so what you see is that with conventional kind of physics-based approaches like Gold and Vina, they do reasonably well, right? That there's not much of a delta between what's chemically valid and what's not. But if you look at deep learning-based methods, they often, even though they look good on paper, once you sort of screen them, the performance drops rather precipitously, right? And the green versus red here is basically, this is the data set that sort of, the pink one is more carefully validated, more carefully stratified, so that you're not sort of, overfitting. You're not testing on the same things you've seen in your training set. And this can be partially covered. I should skip this one. Can be partially covered if you do some physics-based relaxation after the fact, so it's not all a loss. But nonetheless, when you sort of do all this very carefully, what you end up with is that something like diffduct, which was kind of before Rosetta Fold and AlphaFold 3, which was the leading method in this space, it does end up doing worse than the kind of classical physics-based approaches. So now I think what's really interesting, and the most recent developments has been Rosetta Fold or Atom, which does a harder problem, I should say, than like Vina or Gold, because it's trying to predict the structure simultaneously with the ligand, right? So this fully blind docking, you're not giving it a binding site, you're not giving it any prior information. It's trying to do everything from scratch. And on that sort of difficult metric, it does reasonably well. I think the fraction of predictions that are under 2 angstroms is something like 42%. And then now, obviously, most recently with AlphaFold 3, we see yet another leap where this is Rosetta Fold or Atom, again about around 40, and AlphaFold 3 sits around, I think, 78% or so. Now, in the very beginning, I mentioned the kind of value of architectural engineering and so on, and I think here again is sort of revalidated, right? So, they're essentially training on very similar data sets. But the Rosetta Fold or Atom is essentially the AlphaFold 2 architecture, but slightly tweaked. While this is a fairly different architecture, and again with that delta, with the architectural delta, we see doubling of essentially of not accuracy, but actually recovery in this case, doubling of the success rate. So rather significant. I should say that regardless, I do think these numbers are a bit optimistic in the sense that the post-Buster data set is probably a little bit too easy, and I don't think it really reflects sort of true drug discovery programs. So I don't think that if you apply any of these methods, you'll actually, in an actual program, you'll see those same numbers. That's sort of just my expectation. I think these are all a little bit too easy in a way. But let me just, in the last maybe 2 minutes, talk very briefly about AlphaFold 3. So one notable thing here is that it's kind of a general biomolecular system, so it's trying to predict anything, nucleic acids, small molecules, post-translational modifications, and so on. This is the AlphaFold 2 architecture, and its key idea, I think, was the MSA and sort of excessive sampling of this MSA through this sort of approach where you kind of ping-pong between what is essentially kind of a pairwise representation of the structure, like a distance matrix almost, and this kind of MSA representation of the evolutionary history. AlphaFold 3 does away with some of that. So this is the overall architecture. You still have this sort of input embedder, which encodes your inputs, as before. You still have this evoformer-like thing, which does the bulk of the reasoning. But what's critically different now is that this MSA module is shrunken considerably, so it's not spending nearly as much time on it. And instead, most of the time, it's actually spent on this pairformer, which is kind of a lighter weight version of the pairwise reasoning module that it has. And then finally, instead of the structure module, which was this sort of regression-based approach back then to generate the final structure, now, like I said, they do a bit like AlphaFlow and so on, where they condition on the latent representation of the model, of the representation that's been learned by this component of the model to diffuse a structure. Because I'm running out of time, maybe I'll just mention this one kind of highlight and then I'll stop. So it does a few different things in AlphaFold 2, but I think arguably the most important is the way it represents objects, including at the very beginning, at the input embedder. So what AlphaFold 3 does, it's essentially kind of combines a sort of hybrid approach, where it takes the initial structure and projects it down to just all atoms. Right? So it actually operates, at some level on an all-atom representation, which is quite different than AlphaFold 2, which operated at a tokenized or residue level representation. But what's interesting, because that's too expensive, is that it does a sort of hybrid scheme, right? Where locally, when it's in the atomistic world, it's doing attention in sort of neighborhoods. So it's not attending to the entire rest of the structure, but only attending to regions of the structure. But then that operation is used to update a sort of a token level representation where amino acids are a single object and nucleic bases are a single object. Nucleic acid bases are a single object, and atoms in a small molecule are single objects. And then at that level, at that sort of coarse-grained level, the attention is global, just like AlphaFold 2, where everything is seeing everything, right? And I think this sort of hybridization is really quite key, right? Because it achieves data computational efficiency by sort of being local when it can afford to and global when it can, and at the same time, by being data efficient, by essentially kind of unifying the representations of proteins, small molecules, and nucleic acids in one sort of layer, right? Which is not something like, say, Rosetta Fold or Atom had done. And I think that's a key difference. I'll skip the rest of it just so I want to leave some time for questions. I end up going over time regardless. So this is all that. I'll just maybe leave you with this, which is, so obviously we are part of this consortium, OpenFold, and for us, what's been really interesting, right, is thinking about ways in which we can take this in a new direction, right? And I highlight some of these. I talked a little bit about them today, and of course, I should say we are in the process now of beginning to produce AlphaFold 3 because we think that's very important and being able to have it open to this community. Because even if DeepMind does release the model ways, we know they won't be for commercial use, and so that I think will be something of high value to everyone here. Of course, thank all the support that we've received from several companies in getting this up and going, and even just over the years in terms of compute and resources and so on. And then finally, I'll just end with some acknowledgments. This was a huge team effort. Lots of people contributed to this. It started out essentially, as really a work of Gustav and Nazim in my group. Now, since it's included several people, including Jennifer, who's part of OMSF, Christina, Lucas, and other folks in the lab who are working on other pieces of the problem. And this is a snapshot of my lab from a few months ago. Thanks for your attention.